All right, so in this video, we're going to look at reviewing vectors and projectile questions. Let's assume we've already done some work with vectors and projectiles, but we're reviewing to get ready for that test that will be upcoming on vectors and projectiles, what I would call Chapter 2 in grade 11 physics. So let's take a look at reviewing these. What I want to start with is the review of vector questions where you have some scenarios like this, where there's a boat and it's going to be traveling on some water. It might ask where it ends up, how fast it's going, or what direction it should aim so that it gets to its desired location, like a dock or something like that. As these questions, I think the hardest part is drawing the diagram and also visualizing what's happening. So I'm trying to put together some animations here to try and show you what's happening in these different scenarios. Let's start with a super basic scenario where the water is not moving. It's just like a still lake, and the boat's going to drive down at 5 meters per second. And the width of this lake is 50 meters. The question might ask, how long does it take to get to the other side of the lake? Not too bad a question. We go 50 meters at 5 meters per second. It should take 10 seconds to cross the lake. Probably doing okay with that, but let's make it a little bit more challenging now to where the water is going to be moving. So now this is kind of like a river scenario, and the water is moving this direction at 3 meters per second. So if the boat was just, floating in the water, it would drift this way at 3 meters per second. But now let's combine those two motions where it's going to try and drive towards the dock, and it's also going to get pushed by the river. Then the boat's going to follow this direction. It's going to come at me kind of this way, moving at an angle. Okay, so it's important to note the boat doesn't drive down and then get pushed across. It travels along the hypotenuse, along this line. And the first question you might see is, what is its velocity relative to the shore? And even that wording is a bit tough. What's the velocity relative to the shore? Well, first, its velocity, not relative to the shore, but relative to the water, was that 5 meters per second. We saw in the first example, if the water wasn't moving, the boat's driving at 5 meters per second. Relative to the shore means relative to something stopped or not moving, or from this overhead view, how fast do you see it actually going? Going along this line, we can use Pythagorean theorem to say it is going at 5.8 meters per second. Use tan to give its direction at 31 degrees east of south. So that's its velocity relative to the shore. But then the question might ask, well, how long does it take to get to the other side? And it's really common for students to want to use that 5.8 meters per second. But remember, we were driving down at 5 meters per second. This number over here, 5 meters per second. Just because we're getting pushed down to the side doesn't change how fast we're going to that shore. So we'd have to use the 5 meters per second down with the distance 50 meters down, and we'd do the exact same calculation. 50 over 5, it takes 10 seconds to reach the other side. Okay? Now, we didn't reach the dock this time. We got pushed over to the side because as we were trying to drive straight down, we're getting pushed over to the side. So the question might say, how much did you miss by? How far did we get over, or how much did we drift down the shore? And the answer here is, well, as I was driving down, I was drifting to the side at 3 meters per second. 3 meters I drifted east every second. So if it took us 10 seconds to cross, it should have drifted us down 30 meters. 3 meters per second times 10 seconds. Now we're going to look at what's going to happen if you want to reach the dock. But instead of just jumping to that, let's try a couple ones where we're moving in the direction of the water. So first of all, we're in a still lake. Again, we're going to drive at 5 meters per second. We would go at 5 meters per second. That would be 5 meters per second relative to the water, but also 5 meters per second relative to the shore. But now we're going to start to get a little more, hopefully a little more comfortable with the wording when we get the water moving. So I'm going to say the boat's going to drive at now 0 meters per second relative to the water. So they're just parked on the water, but the water is going to be flowing this way at 3 meters per second. Negative because it's backwards. How fast does the boat appear to move relative to the person? Like the person up there standing on the shore. How fast does it look like the boat's moving? Well, -3. They're just going with the water. It looks like they're moving back at 3 meters per second. Okay, let's make it a little bit different. Now let's say that the boat's going to drive at 5 meters per second relative to the water. Okay, so driving this way at 5 meters per second, but now the water is going to be shifting back. It's going to look more like this. You can see from if the boat stopped, we can see it's moving away from where it would have been just floating at a rate of 5 meters per second. But what's it look like from the person on the shore? Well, the person on the shore, I'll show it one more time, seems to be moving forwards, but not as fast as 5 meters per second. We got to take away the 3 meters per second going this way. It appears like they're going at 2 meters per second relative to the shore. That's how fast they're moving relative to the person stopped. Okay, one last one here before we get into angles. Let's say that the boat drives this way at positive 3 meters per second, that way, and the water's flowing at negative 3 meters per second this way. Okay, so once again, we can see the boat is driving forwards on the water, but it seems like it's getting canceled out. It's canceling the 3 meters per second backwards with 3 meters per second forward, so it appears to be staying in the same position relative to the shore, so it's going at 0 meters per second relative to the shore, even though we're still moving forwards compared to just if we're just floating on the water. This scenario is actually really important because in the first example, we were trying to get to the dock, we ended up drifting downstream. But now if I want to make sure that I stay in line with the dock, I need to cancel out the movement of the water, just like we did in this example. Go back here, cancel out the movement of that by driving 3 meters per second this way if the water's pushing me back at 3 meters per second this way. So now if we don't want to just sit there, we want to get to the dock that's down here. I'm going to take the boat, here we go, and I'm going to angle it so that part of it is driving into the flow of water, and I'm going to cancel out that 3 meters per second. So I want to turn the angle of the boat so that I would be going that way at 3 meters per second. That component of my velocity is 3 meters per second, so it cancels out the negative 3 of the water. If we can do that, just move the 5 meters per second out of the way, it's the same diagram, we'll just travel directly to the dock or our location with X here. And we follow this straight line. So we don't go there and then come back, we actually follow that line vertically down. So that's how we reach the dock. It could ask two things. One, how long does it take to get there? But this time we're not going to use the 5 because the 5 isn't going directly to the dock. We're going at 4 meters per second. How do we get the 4? Well, it's Pythagorean theorem. 5 squared minus 3 squared square root could give us that 4 meters per second. So to calculate how fast we're getting to the dock, I'm going to go back to here. We're moving towards it at 4 meters per second. So we'd have to do 50 divided by 4 meters per second there for the time. The other question they could ask is, what angle did you have to turn your boat at? Where should I point? And we'd have to point 37 degrees west of south. And we get that number from using inverse sine of 3 over 5. I thought I'd just show one more way to show that we are actually driving at an angle on the water, but it's getting canceled out. So this diagram is really the same. I'm aiming at an angle that way, and hopefully this shows relative to if I was just floating there, we are driving the boat at an angle, but because it's getting pushed back, our resulting velocity is just directly towards the dock. So this picture works well if you like that as well too. The water pushes me this way, we counter at an angle, and the resulting velocity is directly down at 4 meters per second. Okay, you'd solve for 4 meters per second the same way, you'd solve for the angle the same way, it's just another way to visualize it. So I hope that's helping you with visualizing what's going on in these vector problems. Okay, the second part of chapter 2 that could be on this chapter 2 test is projectiles. We have horizontal ones and vertical ones. First, just going over the theory again, I want to show what's happening in both the vertical, what I'm going to call the y direction, and the horizontal, the x direction. So we're going to have a horizontal projectile, which just means the biker in this example is going to go horizontally and then into the air off the ledge. So we're coming horizontally here and then off the edge. Now I see this probably looks a little bit confusing. What I'm trying to show here is the orange is what's going to happen in the up and down. And it's just that they start up top here and fall just like it's being dropped. What's happening in the X or the side to side direction is this is supposed to be kind of following them along this way. They just move at a constant velocity. So I'll show that one more time. I'll get out of the way here. It's going to go and it's like it gets dropped in Y and just keeps moving across in X. Okay, so I'll even put that with some arrows. We have constant motion here, or uniform motion, but then accelerated motion in Y. That's the big theory idea for horizontal projectile questions. And it's pretty similar for vertical ones as well. It's just got an initial velocity up. Let's take a look at that one here with this snowboarder. Again, I'll get out of the way. We'll look at these shadows and it jumps up in the air and then comes back down. Okay, so the blue here was supposed to show that it goes up and then comes back down with my messy arrows here. That's the motion that occurs in Y, or the vertical. But then the green one, again, just going side to side, is going to stay at the same velocity. So let's look at that one more time. I'll step out of the way. And it goes up. The blue goes up and down, just like an object thrown up and down. And green keeps moving equally to the side. So we can see green is going equally to the side here. But then in Y, it's going up and then back down. I'm going to do some quick examples of how to calculate that just to show how we put that theory into practice. Let's start with a horizontal projectile question, and here's that biker coming off of the ledge. Let's throw some numbers that they gave you. Say they give you the numbers of they're going at 5 meters per second off the cliff. The cliff is 3 meters tall, so they fall 3 meters. How far do they end up going to the side? And we'll assume they land safely. They're a very good biker. All right. So first thing I would ask is this question mark, is that in my X side to side or my Y up and down? And that's a distance in my X side to side. So let's start looking in X. We said that's always going to be uniform motion. Formula is V is equal to D over T. Perfect. I'm solving for the distance. Only got a couple variables. I'm going to rearrange and do my distance, or I should say displacement, is 5 times the time because it's 5 meters per second, but I don't have the time. And this is a really common scenario that we run into for projectiles. But fortunately, the same time that we're moving to the side is the same time that we're falling. So if we get the time of the fall from Y, it should be the same one. Let's go over into Y. Can I use V is equal to D over T? No, because it's accelerated motion, accelerated by gravity. So to figure out what equation to pick, let's list all our variables. VI, VF, A, D, and T, all the accelerated motion variables. Fill in what I know. VI is 0. That's an important part because lots of people think 5 meters per second, but it wasn't launched up or down. My velocity in the up and down started at 0, and then it became negative. So I don't know what it was. VF, when it hit the ground, I didn't know. But it accelerated downwards at 9.81, fell -3, and I'm here to solve for time. So I want to solve for time. I don't care about VF because I don't need to solve for it, and I don't know that information. So let's book the equation without VF. There's this one here, D is equal to VIT plus half AT squared. That's a tough formula to solve for time because I have a T and a T squared, and we're not going to do any quadratics at this grade 11 level, so we're not actually going to have to plug in or rearrange that equation. How could we make it easier? Well, VI is 0. 0 times whatever the time is going to be 0, and that doesn't change it when we add that number. So if time was 1, 0 times 1 is 0, and it won't add to change our number. So it doesn't matter what that is there. We can cancel out VIT since VI is 0. That makes it much easier to rearrange here. We'll times by 2, divide by A, and square root to get our time. If you plug those numbers in, we should get 0.782 for our time. Okay, we're not done because the only purpose of getting that was so we could go back into X. So let's take that number and let's throw it over into X. 5 times 0.782, and we do get our final answer of 3.9 meters is how far they landed away from the ledge. Let's finish off with an angled one where really all that's going to change is now we do have an initial velocity in Y. So we can see the snowboarder doing a nice flip here off a ledge, off a jump, and landing a little bit further away from the ledge in this case. Let's see what happens. So once again, I'm going to look at the values they give me. It launched at 5 meters per second, fell 4 meters this time. How far did we go in the X direction? So if it's asking me for X, I'm going to start very similar. In X, it's still uniform motion. Even though I was launched upwards, it's still moving at uniform motion in this direction. So V is equal to D over T. Nothing's pushing or pulling it there after it's launched in the air because we're ignoring air resistance. Okay, now at this point you might think, okay, perfect, 5 times our time. We're going to do it just like last time. However, the 5 is now not the velocity in our X direction. The 5 is at an angle of 40 degrees. So I need to figure out how fast I was moving in this direction by breaking it into its components. How far we're moving in X and how fast we were launched upwards in Y. So we'll do that. And we use sine and cos. I get 3.83 and 3.21. So it's important we put that 3.83 in for X, not the 5 meters per second. Okay, so that's a change from when we get to angled ones. After that, it's going to be looking pretty similar here because I still need time. Let's go over to Y, list my variables. They look pretty similar, but I do have a value for VI. That may seem like not much of a big change. It's kind of still more information, but it makes it so that if I do the same process as last time and try and use VIT plus half AT squared, well, now I can't cancel VIT. Can't cancel VIT because VI is a number, 3.21, and so I'll have to rearrange for T using a quadratic. And we're going to avoid quadratics in this course, or at least the way that I teach it. So then how can we solve this question? Well, let's not use that one. Let's solve for VF instead and then we can solve for t after. So an extra step here for solving for VF. So equation without t is VF squared plus VI squared, equals VI squared plus 2AD. We'll rearrange that just with a square root and get negative 9.42. Now, it's possible that your calculator gave you positive 9.42. It's actually very likely that it gave you positive 9.42, because whenever you take a square root, it's going to give you a positive answer. But the square root, we never really write this part. Let's see if I can get my pen. There's a plus or minus symbol in front, because when you take the square root, the positive or the negative answers are possible. Because if you have 2 times 2, that's 4, and negative 2 times negative 2, that's also 4. So the square root of 4 is positive 2 or negative 2, both times by themselves to give you 4. So similar here, my answer gives me 9.42, but it could be the plus or minus version. That's a really important part to remember for this test. Make sure you make that negative if in the picture it's falling down, which in most scenarios it is. Okay, so next I need to solve for my t here. I didn't change my variables over on the side, but I'm looking for t. I think the easiest equation to solve for t there is our first kinematic equation. A is VF minus VI over t. Nice, because all I have to do is switch out the A and the t here, plug in my values, and my time becomes 1.287. Once again, I'm going to note, make sure you're putting in, wherever my mouse is here, there it is, the negative 9.42 here, and the VI being positive in there. That's going to make sure that you get this answer, and divide by a negative 9.81. That should give you that positive value for time. Okay. After that, we're just about done. Let's take that number for time and throw it back in for x, our speed in x, multiplied by the time, and we get a bit of a larger distance here. dE is equal to 4.9 meters. Okay, so that's it we have for this video. Thank you so much for watching that. I hope it helped you understand and review those Chapter 2 concepts. Good luck on your test, and I will see you in the next video.